Hello everyone, welcome to this short video on example problems from limits and continuity. So in this video, we are going to work on a couple of examples on how we can handle the limit problems. So let's begin with our first example here. So here is our first example. Complete the table below. Here is the table given, okay? For this function, f of x equal to x plus 3 over the square root of 6 minus x minus 3. So if you look at these numbers here, we have x values, negative 3.1, negative 3.01, negative 3.001. That means if we look at this closely, what we see is these numbers are getting closer and closer to negative 3. We have negative 3.1, negative 3.01, negative 3.001. So you can see that these numbers are getting closer and closer to negative 3 from the left side. Also, if we look from the other side, we have negative 2.9 here, negative 2.99, negative 2.999. So we are also approaching negative 3 from the right. And we have to complete this table. And we are writing all these values up to 4 decimal places. So what is the meaning of that? Let's see. First one is when x equal to negative 3.1, what is the value of the function? That is the meaning. So what we are doing is we are plugging in negative 3.1 into this function. So we are basically calculating f of negative 3.1. So f of negative 3.1, when I plug in negative 3.1, this is going to be, so x is negative 3.1, then plus 3 over the square root of 6 minus x is negative 3.1. So 6 minus negative 3.1, and then minus 3. So now we can rewrite this as negative 3.1 plus 3 over the square root of 6, and then we have negative and negative, that makes positive. So 6 plus 3.1, and then we have minus 3. So we need to simplify this one. So the best way you can simplify this is you can type this in your calculator and then find its value. So if you plug into your calculator and check it, you should get negative 6.0166. So the value that we obtain here is negative 6.0166. We'll repeat the process as we move from negative 3.1 to negative 3.001. So now, if you plug in negative 3.01, okay, if you plug in negative 3.01 into this function and simplify, you'll get negative 6.0017. And again, if you plug in negative 3.001, then you'll get, make sure you plug into your calculator and check it, you should get 6.0002. So if we observe this carefully, what we see is when x approaches to negative 3 from the left, the value of the function, this function, approaches to 6. We have negative 6 point, approaches to negative 6. Here we have negative 6.0166. Now it becomes negative 6.0017. So very close to negative 6 again. And now it is still closer. So what we can say is limit from the left-hand side. We write it like this. Limit as x approaches to negative 3. Okay, negative 3 from the left of that function is equal to negative 6. So the left-hand limit is negative 6. Now, let's repeat the process by plugging in the values from the right. So say, for example, if we plug in negative 2.9, what happened? It is the same process. You plug in x equal to negative 2.9. So f of negative 2.9 is equal to negative 2.9 plus 3. And in the denominator, same thing, square root of 6 minus negative 2.9. And then you have minus 3. Then if you simplify, negative 2.9 plus 3 over the square root of 6, we have a negative and negative here. That makes positive 2.9, then minus 3. Now, we can again use calculator to simplify this. If you use calculator and simplify, you should get negative 5.9833. Okay, so the value for this one is negative 5.9833. We repeat the process now. If you plug in negative 2.99 into this function, you should get negative 5.99833. Similarly, if you plug in negative 2.999, you'll get negative 5.9998. So if you observe this carefully, what you'll see is the limit when x approaches to negative 3 from the right, from the values that are greater than negative 3, so that's a right, of the function is equal to, you can see negative 5.9833, 5.9983, 5.9998. That means these values are also approaching negative 6. So this limit is also negative 6. So meaning of that is your left-hand limit and right-hand limit are equal. Okay, so this is the left-hand limit, this is the right-hand limit. Limit from the left side and limit from right sides, the right side are equal. So it means that the limit as x approaches to negative 3 from both sides, it exists. Okay, for the limit to exist, left-hand limit and right-hand limit must be equal. So here the limit exists. And the value of the limit will be equal to negative 6. That means here we are asked to estimate the limit for this function, the same function which is here, that is equal to negative 6. So this is how we can find the limit of the function like this using the method laid out here. So in this method, we use the numbers. So this is called the numerical method or a table method. So we can basically use the numerical method to evaluate the limit. We are going to look at one more example, which is similar to this one. Here is that example. Complete the table given below for this function, f of x equal to sine 8x over x. Round your answer to 6 decimal places. In the previous example, we are asked to go up to 4 decimal places, but here we are asked to do it up to 6 decimal places. Now, one quick note here, because you can see that here we have the trig function, sine 8x over x. So because we have this trig function, if you are using calculator, make sure you use your calculator in radian mode. Okay, we have to use the angle in radian. That is very important. Please note that you use the calculator in radian mode. So just like in the previous one, if you look at these numbers carefully, you can see that we have negative 0.1, negative 0.01, negative 0.001 up to here. So what we can basically see is these numbers are going closer and closer to 0 from the left side. Similarly, if we look at these numbers, 0.1, 0.01, 0.001, we can also see that these numbers are also getting closer and closer to 0 from the right. So from this side, the values are increasing and approaching 0. And from this side, the values are decreasing and approaching 0. And we have to complete the table. Process is same as before. So what we do is to find the value that goes here in this box, we plug in negative 0.1 radian into this one. So f of negative 0.1 is equal to sine 8 times negative 0.1 divided by negative 0.1. Remember, this is 8 times negative 0.1. So if we type this in the calculator, you can type this in calculator and check it. You should get 7.173561. That is the first value. that goes in this first box. So let me write that down. We get 7.173561. And we repeat the process. Now, if you plug in negative 0.01 into this function and simplify, you should get 7.991469. Make sure you use your calculator and verify that you get that, okay? And then let's plug in negative 0.001 into the same function. You should get 7.999915. So clearly what you can see here is when x approaches to 0 from the left, the value of the function, these values are increasing and approaching closer and closer to 8. So we can say that the limit as x approaches to 0 from the left of the given function is 8. From the left side, the limit is 8. So we repeat the process and we find the limit from the right side. So if we plug in, let's say, if we plug in this number, 0.1 into the function, it will be sine of 8 times 0.1 over 0.1. And then if you simplify this using calculator, you should again get 7.173561. Because this function is symmetric about y-axis, we get the same value. So we get 7.173561. Similarly, if you plug in 0.01 into this function, you should get 7.991469. And if you plug in this third number, you'll get 7.999915. So just like on the left-hand side, we have the same values on the right. So as the values of x are decreasing and approaching 0, the function values are increasing and approaching 8. So we can say that limit as x approaches to 0 from the right of the function is also equal to 8. And clearly, the left-hand limit and right-hand limit are equal. So we can say that the limit as x approaches to 0 of the function exists. Okay, and that limit is equal to these two limits, the left-hand limit and right-hand limit. They are equal. So that means the value of this limit, which we are asked to estimate here, limit as x approaches to 0 of sine 8x over x must be equal to 8. So one more time, this process of finding the limit using actual number, plugging in the number into the function and analyzing the pattern from left and right, this is called the numerical method of computing the limit. That is the second example for today. Okay. Now let's move on to third example. Here is our third example. We are asked to find the limit as x approaches to -5 of sine -3 pi x. So basically what we do is in this type of problem, we can find the limit by direct substitution. Direct substitution is one of the process of finding the limits. So you can see that here we have limit as x approaches to -5 of sine -3 pi x. So because there is no denominator or radical, you are safe to, make a direct substitution here. So if you try to do that, the value of the limit will be sine -3 pi multiplied to x is -5. So you plug in -5 for x. This is -5. And if you multiply, it will be sine 15 pi. And you should know the value of sine 15 pi from your unit circle. So let me quickly remind you about that unit circle. Basically, let me first draw it completely. Then I'll start talking about it. So in unit circle, over here, if you think of the coordinate over there, that is 1, 0. 1 comma 0. So cosine 0 is 1, sine 0 or sine 0 pi is 0. And then if we come here, that is negative 1, 0. Okay, so cosine is negative 1, but sine is 0. So sine is 0 at 0 pi. 0 pi is same as 0. And when you come here, this is 1 pi. At 1 pi, it is 0. If you go here again, at 2 pi, it is 0. Come like that. At 3 pi, it is 0. Go like that. 4 pi, it is 0. So whatever that number may be, 1, 2, 3, 4, whatever that may be, for all multiple of pi, the value of sine is 0. That means this limit is equal to 0. So very simple one. All you need to do is you plug in the given x value into the function, and then you use the unit circle to evaluate the trig function over there. So in this one, the value of the limit is 0. Okay, that is our third example. Let's move on to fourth example. Example 4. So this is our fourth example. Okay. So in example 4, you can see that there is a step function given. I mean, piecewise defined function is given, okay? And we are asked to find the limit. So if we look at it carefully, f of x is equal to cosine x minus 4 if x is less than 4, and then e to the x plus 4 if x is greater than or equal to 4. So basically, if you try to, analyze this in little bit detail, you can draw a number line like that. You can represent 4 here. And then if the value of x is less than 4, you can see if x is less than 4, the function for this interval will be cosine x minus 4. It is cosine x minus 4 on this interval. And on this interval, including 4 and more, x is greater than or equal to 4, is e to the x plus 4. This side, it is e to the x plus 4. Now, the question here is, we have to find the limit. See, we have to find the limit as x approaches to 4 from the left. This minus sign means from the left of the function. So we are approaching 4 from the left. We are getting closer and closer to 4 from this side. That means our function, as we approach from this side, our function is cosine x minus 4. So that is the function that we want to use here. So that is same as, okay, this is same as the limit as x approaches to 4 from the left of cosine x minus 4, right? From the piecewise defined function, for our value here, x approaches to 4 from the left, it is cosine, so cosine x minus 4. And one more time, because it does not have the denominator or radical, you are safe to make that direct substitution. So as x approaches to 4, you can plug in 4 for x. So this is going to be cosine 4 minus 4, which is equal to cosine 0. And you know from the previous example over here, cosine 0 is this one, which is 1. The cosine 0 is 1. So the limit for this example is 1. So you can clearly see that for this type of problem, we can find the limit by direct substitution. We can make direct substitution, and then we can find the limit. But remember, because this function is piecewise defined function, you must know which piece to pick up when you calculate the limit here. In this one, because we are approaching from the left, we take that piece. If it was from the other side, we would pick this one, e to the x plus 4. Okay, that is example 4. Let's move on to example 5 now. Example 5 is also a piecewise defined function. And then you can see that this function is defined for x less than 1 and x more than 1. So just like in the previous example, if you want to draw a number line and represent that, just to make your life a little easy, that's totally fine. So there is your 1. And then we want the limit as x approaches to 1 from the right. But first, we are going to represent this function in the number line. So for x less than 1, as you can see, for x less than 1, the function is tangent x minus 1. It is tangent x minus 1. And for the value of x, which is 1 or more, it is sine x minus 1. It is sine x minus 1. And what we are asked to do is we are asked to find the limit as x approaches to 1 from the right. Limit as x approaches to 1 from the right of the function. That is our question. So when x approaches to 1 from the right, so as we are approaching from this side, our function is sine x minus 1. So we do limit as x approaches to 1 from the right of sine x minus 1. So we pick sine because we are getting closer and closer to 1 from the right. And as we approach from the right, our function is sine x minus 1. So now, because it does not have the denominator, it does not have the radical, you are safe to plug in the value. So we can make direct substitution here. So it will be sine x approaches to 1, so 1 minus 1. That becomes sine 0, and you know that sine 0 is 0. So the limit of that function, this function given here, when we approach to 1 from the right is 0. That is your fifth example. Okay. Now let's move on to sixth example. Now this one involves the absolute value. Limit as x approaches to 6, okay? And this is from the left, x approaches to 6 from the left of this one. So remember, absolute values are the functions that make everything positive. So here we have absolute value of x minus 6 over x minus 6. And if you think of this value, x minus 6 and x minus 6, they will be equal, right? They will be equal. Absolute value of x minus 6 in the numerator, x minus 6 in the denominator. So magnitude-wise, they will be equal. But this numerator is always positive. Look at that. Numerator is always positive. Okay? And when x approaches to 6, if you think of a number line, and then you have a 6 here, when x approaches to 6 from the left, if we go from this side, x will be smaller, okay? X will be smaller than 6. So denominator will be negative. So they are approximately equal. Numerator is positive, denominator is negative. That means when you divide the equal quantity, it will be 1, but denominator is negative, so that will be minus 1. Minus 1 if x is less than 6. But if we go from the left side, right side, okay, if we go from the right side, or if we go from the positive side, then they will be just equal. Both will be positive and they will be equal. So that means it is 1 if x is greater than or equal to 6. So what we clearly see is this function is same as this one here. And then if x is less than, you can clearly see, if x is less than 6, the value of the function over here is 1. Okay. And on the other side, the value of the function, if it is less than, it's negative 1. And then on the other side, if x is greater than or equal to 6, it is positive 1. It's positive 1. So you can clearly tell the limit. So in this case, the absolute value of x minus 6 over x minus 6 is negative 1 when you approach from the left side. So we can say that, we can write like this, limit as x approaches to 6 from the left of absolute value of x minus 6 over x minus 6 is same as the limit as x approaches to 6 from the left, and this quantity is negative 1. And from the limit law, you know that limit of the constant is just that constant, which is negative 1. So that limit is equal to negative 1. So this is how you can find the limit involving the absolute value. Okay, so it's not that difficult, but you should analyze the function first and understand the value of the absolute value. Okay, the absolute value function can be negative 1 or positive 1 here because the numerator and denominator are same. And here the boundary line is 6. So you have to check for the values less than 6 and values more than 6 first. Okay, so that is our sixth example. Now let's move on to seventh example, which involve little more math compared to this sixth example. Okay, here comes the interesting one. So we have to evaluate this limit as x approaches to 0. If you remember in a couple of examples before, I was telling you, you can make direct substitution if there is no fraction or no radical. But this one has a fraction and also radical. Why we cannot make direct substitution maybe? Let's see. If you plug in 0, you'll see that the denominator will be 0. And remember, in a fraction, you cannot have denominator 0. So we cannot have 0 in the denominator. In fact, this becomes, if you plug in 0, numerator will become 0 and denominator will be 0. It will be 0 over 0, which is indeterminate form. So we cannot make direct substitution like that. And here, the problem is because of this x. We cannot have 0 in the denominator. So somehow, we need to remove this x from the denominator. So let's see what is that technique. So here we have limit as x approaches to 0 of square root of x plus 5 minus square root of 5 over x. So what we need to do here is, because it involved the radical, we need to multiply by the conjugate. We have radical in the numerator, so we have to multiply by the conjugate of the numerator. Conjugate means you change the sign in the middle. You have x plus 5, then plus 5, plus square root of 5. Square root of x plus 5 plus square root of 5, like that. So we multiply by the conjugate. See, here is a minus, so we take plus. And we multiply by same quantity in the numerator and denominator. So this is like basically we are multiplying by 1. And if we are multiplying by 1, we are not changing the value of the limit there. That's why we are safe to multiply by 1. Because this will help you to remove that x from the denominator. And it will make it easy for us to simplify this. So we have limit as x approaches to 0. We are multiplying two fractions. This is one fraction multiplied with the other fraction. When you're multiplying the fraction, you know that we can multiply denominator with denominator and numerator with numerator. So in the denominator, we have x multiplied to that quantity. So I'll write like this, x multiplied with square root of x plus 5 plus square root of 5. And in the numerator, you can see that when you multiply these two, you can basically FOIL it and you can do it. Or you can also think of this one. See, this quantity and this quantity, they are the same. And the second quantity and second quantity are the same. One is minus, other one is plus. So it looks like a minus b times a plus b. So if you remember from factoring, from your pre-calculus, a minus b times a plus b is a squared minus b squared. So basically, when you multiply this quantity with this one, it will be in that form a squared minus b squared. So a squared means square of the first quantity, which is square root of x plus 5 squared. And then minus b squared means square root of 5 squared. The second quantity is squared. So that will be equal to limit as x approaches to 0. Now in the numerator, square and square root cancel here. So that becomes x plus 5. And then minus, same thing here, square and square root cancel. So that will be 5 over the denominator. We'll keep it as it is. X times the square root of x plus 5 plus square root of 5. Okay. Now, if you look at the numerator carefully, you'll see that 5 get cancelled there. 5 minus 5 is 0. So that get cancelled. So we get limit as x approaches to 0, x in the numerator, and then in the denominator, we have x times the square root of x plus 5 plus square root of 5. Nice and easy. Now, everything is in multiplication. This quantity x multiplied with that, with this quantity inside the bracket. And in the numerator, you have x. But if you look the other way around, this is like x over x, or x divided by x, which is 1. So we can rewrite this as limit as x approaches to 0, 1 over the square root of x plus 5 plus the square root of 5. Now see, we start with this question up here. There is x in the denominator. So if we make direct substitution, denominator will be 0. So we cannot plug in. But what we did is we multiply by the conjugate and we simplify that. Once we do that, when we get into this step, that problematic x from the denominator got canceled. So we don't have anything that causes problem now. So what we can do is after this, we can make direct substitution. So if you make direct substitution, it will not make denominator 0. It will be square root of 1 over square root of 0 plus 5 plus square root of 5, which is equal to 1 over square root of 5 plus square root of 5. That's plus. Right? 0 plus 5 is 5. So that is with this square root, which is equal to, which is same as 1 over 2 square root of 5. That's our answer, but we have radical in the denominator. So we multiply by square root of 5, and then we rationalize the denominator because we don't leave radical in the denominator. So multiply by square root of 5 just to simplify that. So if you multiply like that, both numerator and denominator by square root of 5, you get, again, two fractions multiplying. We multiply numerator with numerator. 1 times square root of 5 is square root of 5. And then square root of 5 times square root of 5. That's a 5 times 2 is 10. So the limit for the given problem as x approaches to 0, right? When x approaches to 0 and we find the limit of this one, we get square root of 5 over 10. So remember here, this is a little long problem, but if it involves radical like this, okay? If the problem involves radical and the denominator will be 0, what you have to do is you always have to multiply by the conjugate and then simplify. And once you're done simplifying, you just plug in the value of x and you get the limit. So it is just that easy. Although it's long, if you remember the process, it is not difficult. Okay, that is number 7. Now let's move on to number 8. So problem number 8 here, evaluate the limit. So again, if you look at this carefully, see, limit as x approaches to -1. If you plug in -1 here, so it will be -1 plus 1, that will be 0 again. So we cannot do the direct substitution here. We have limit as x approaches to -1 of x squared minus 1 over x plus 1. So denominator is 0. So somehow we have to cancel this x plus 1. But if you look at the numerator, we have x squared minus 1, which is just like a squared minus b squared. Difference of 2 squares, because 1 is same as 1 squared. And if you remember from pre-calculus, we can factor these to a plus b times a minus b. So we can rewrite this as the limit as x approaches to -1, x minus 1 times x plus 1. And in the denominator, you have x plus 1. So clearly you can see that these two get canceled because x plus 1 divided by x plus 1 is 1. So that get canceled there. That problematic x plus 1 got canceled, and we get limit as x approaches to -1 of x minus 1. Now what we obtain here is a linear function. No denominator, no radical, right? That means in this one, we can find the limit by direct substitution. So we can substitute x as -1 here and find the limit. So in place of x, -1, then -1, which is equal to -2. So there are two techniques to remove 0 from the denominator. Like in the previous example here, if it involved radical, you can multiply by the conjugate, and then you remove that problematic x from the denominator that causes 0, and you can find the limit. But if you have something like that, no radical, but when you plug in this one, x as -1, denominator will be 0, you can factor and cancel that denominator. Okay, so factoring is another technique of computing the limit. So that is your 8th example. Let's go to example 9. So example 9, you can clearly see this involves radical. And let's see whether it will be 0 or not when we plug in. See, we have limit as x approaches to 1. So if you plug in 1 in the denominator, that becomes 1 minus 1. 1 minus 1 will be 0. So definitely in this one also, we cannot make direct substitution. So let me write that. We have limit as x approaches to 1 of square root of x plus 3 minus 2 over x minus 1. So because we are getting 0 in the denominator, and this problem involves radical, we have to multiply by conjugate. We have to multiply both numerator and denominator by the conjugate of the numerator, like that. So when I say conjugate, I have to change the sign in the middle, so that will be plus. And when you multiply here, we have to multiply both numerator and denominator by the same. That is, we are basically multiplying by 1, and we are not changing the value of the limit. Again, we are multiplying the fraction. So we multiply denominator with denominator and numerator with numerator. So when I multiply the denominator, I'm multiplying x minus 1 with this giant quantity. So I'm going to write it like this, x minus 1, and inside the parenthesis, the next quantity, square root of x plus 3 plus 2. And when you look at the numerator now, the first one is same as first, the second one is same as second, and then we have a minus and plus. So if you remember that factoring formula again, a plus b times a minus b is a squared minus b squared. So we'll follow that. So the first quantity a squared, that is x plus 3 squared, minus b squared, that is 2 squared. Now, let's try to simplify and see what we get. Remember, our ultimate goal is to cancel this x minus 1, that is making the denominator 0. So in the numerator, square and square root cancel. You get x plus 3, and then minus 2 squared is 4. I will keep the denominator as it is, x minus 1 multiplied with the quantity x square root of x plus 3 plus 2. Okay. So this is the limit as x approaches to 1. And if you look at the numerator carefully, we have x, and then we have 3 minus 4. 3 minus 4 is negative 1. So we get x minus 1 in the numerator. In the denominator, we have x minus 1 multiplied with the quantity square root of x plus 3 plus 2. Okay, now see that problematic x minus 1 now get canceled because x minus 1 over x minus 1 is 1. So what we get is limit as x approaches to 1, 1 over the square root of x plus 3 plus 2. Now you can perform the direct substitution. Now you can plug in x equal to 1 here and get the result, because this will not make 0 anymore. So this will be square root of 1 plus 3 plus 2, which is equal to 1 over 3 plus 1 is 4, and square root of 4 is 2. So we have 2 plus 2, which is 1 over 2 plus 2 is 4. So the limit is 1/4. So that is how we can solve it. That is the 9th example, which is same as the 7th example that involved radical. So whenever it involves radical, multiply by the conjugate, and then you simplify that. So that's how you can find the limit easily. Okay, now we'll move on to the last example for this video. 10th example here. And this is the use of a squeeze theorem, a special type of theorem to find the limit. So you can see that we are asked to find the limit as x approaches to 2 of that function, where that function is squeezed between other two functions. So what is given here is 7 minus the absolute value of x minus 2 is less than or equal to f of x is less than or equal to 7 plus the absolute value of x minus 2. So meaning of that is the function f of x is squeezed between this function and this function. So this function f of x is more than this, but less than this one. That's why that is squeeze between those two. Now what we need to do is we need to find the limit. So what we do is we take the limit for this function, which is below f of x, and also we have to take the limit for the function above f of x. Or in fact, we can take the limit for this function on the lower end, function on the upper end, and function in the middle. So I can rewrite it like this. So this implies limit as x approaches to 2 of 7 minus the absolute value of x minus 2 for this piece when we take the limit, then less than or equal to, we take the limit for this function, limit as x approaches to 2 of f of x is less than or equal to, we take the limit of this side, limit as x approaches to 2 of 7 plus the absolute value of x minus 2. Then after that, if you look at the lower end here and in the upper end there, we can find the limit of this one by direct substitution because there is no denominator to make it 0 or there is no radical. So we can directly substitute and find the limit. So if we substitute, it will be 7 minus the absolute value of 2 minus 2 because x is 2, 2 minus 2 is less than or equal to limit as x approaches to 2 of the function is less than or equal to. So when you substitute 2, it will be 7 plus the absolute value of 2 minus 2. So that means on this side, what I'm getting is absolute value of 2 minus 2 is 0. So 7 minus 0 is 7. 7 is less than or equal to limit as x approaches to 2 of the function, which is less than or equal to, on the other side, again, 2 minus 2 is 0. Absolute value of 0 is 0. 0 plus 7 is 7. So that is what we get. So if we look at this carefully, you'll see that the limit of the function, limit as x approaches to 2 of the function, it's saying that it is greater than or equal to 7 or less than or equal to 7. Meaning of that is, in fact, it is 7. On the lower end, it is 7. On the upper end, it is 7. So we can say that by squeeze theorem. So this is guaranteed by squeeze theorem. So we can write that by squeeze theorem, limit as x approaches to 2 of that function is also equal to 7. So that is how you can apply the squeeze theorem. Remember, to apply the squeeze theorem, you find the limit for the function that is below the squeezed function and limit of the function that is above the squeezed function. If those two limits are equal, like in this case, we get 7 and 7. If those limits are equal, then the limit of the squeezed function is also equal to that limit. So here in this case, by squeeze theorem, we get the limit as x approaches to 2 of the function is also equal to 7. So this is the end of this video. I hope you find this video helpful. Thank you so much for watching.